Good morning. Welcome to Krishna's Glossary. So last lecture we proved that LP is complete. This was our broad objective when we started, because we were looking at similar spaces with Lebesgue integral replaced by Riemann integral. Then we found that the space is not complete. The corresponding space is not. That means, there are more classes of functions which are Lebesgue integral. And with that observation, we find that the Riemann integrable functions with on some intervals with LP structure is not sufficiently large for completeness. Now this was the problem that anyway, let us recall the NISER theorem and then go for some equivalent conditions of the convergence. So let me just recall the NISER. Let measurable so these are the assumptions that we then LP is a Banach space, by which you mean that all Cauchy sequences in LP converge. That's the meaning of the statement that LP is a Banach space. Okay, so all Cauchy sequences in LP converge to some function which is also in LP. Okay. Further, if Fn converges to F in LP, then a subsequence we have shown how we construct this particular subsequence of Fn converges pointwise almost everywhere on E. Now this is the NISER theorem. Now you can say that there is a subsequence of Fn which converges pointwise almost everywhere on E to the function F. If Fn converges to F in LP. Now we look at some example where you see that there is no LP convergence, and we search for the reasons for that. So let us consider the example. Let E be interval 0, close bounded interval 0, 1. Infinite. Or rather, now we take Fn defined by Fn x n to the power 1 by the characteristic function of the interval 0 to 1 by 0 not included. Now this means this is the function 0 to 1, this is 1 by n, say. Then this function is defined as zero here, 0 at this point, and mark that it is 0 here. The function is defined as n to the power 1 by p, and this is the function where this is equal to n to the power 1 by, this is this one, so n to the power 1 by. Okay. Now this is Fn. Now Fn zero. That is, there is pointwise convergence to 0. That is Fn pointwise to F, which is identically on 0. Now we claim that pointwise convergence does not guarantee LP. LP. Now this is the important point, because in this example you see that Fn converges to F, which is identically equal to 0 point. However, integral 0 to 1, this is equal to 1. Norm of Fn minus F zero. So Fn does not converge to F. So that's the observation that we make about this example. Okay. Therefore, one of the questions that you can ask, suppose you have a there exists a sequence Fn for every n which converges pointwise almost everywhere a function f does it mean, suppose there exists a sequence Fn belonging to LP for every n which converges pointwise almost everywhere to a function f belonging to. Now the question that you ask is this: does Fn converge to f in the LP? That's the question. That's the question that we ask. Now the answer is no. For example, in the example we have considered, discussed, Fn converges to f which is identically equal to 0 pointwise. On 0, 1. However, Fn does not converge to F where E equal to interval 0. So this is what we have observed in this example. Okay. So it suggests that possibly you need more conditions to assure. So mere point-wise convergence to F, which is LP, is not enough to guarantee that Fn converges to F. So Fn converges to F in F belonging to LP is not this is pointwise. So Fn converges to F pointwise almost everywhere to an F belonging to LP is not enough to have no. So that is what this says. So probably we need more conditions. More conditions other than pointwise convergence. Pointwise convergence. So let us suppose this is just mere investigation. Then we have norm of P naught goes to 0. But norm of Fn is less than or equal to which goes to 0. That implies norm of S infinity. Now this is what we infer from. That means a necessary condition for LP convergence is that norm Fn converges to norm F. Okay. So the question that you ask at this stage is this. Is this also a sufficient condition? See how the questions are emerging. Condition. Is this also a sufficient? Now let us in fact prove that this is indeed a sufficient. Okay, so let us prove the theorem. The answer is yes. So let us take the theorem. Let E be a measurable set and one suppose Fn is a sequence LPE that converges pointwise almost everywhere on to F belonging to then we prove that what we have observed is a necessary and sufficient condition for LP. Then if and if limit that is norm of to the power p equal to which is equal to norm f, it's the p norm to the power p. So this is a necessary and sufficient condition. That means this part is a necessary and sufficient condition. That is norm of Fn this is a necessary and sufficient. Already we have seen that it's a necessary. So let us now prove this theorem. Let's prove this theorem. Let us designate by E itself the set after excising a set of 0 where possibly so we assume now hereafter we will use E as the set on which at every point there is a pointwise convergence of Fn2. Thus on E everywhere. So you see that the proof can be done on this, and then what you do is you take the set and remove from it a set of measure 0 where this does not happen, and on the complement of that you do it. Since you are working on the integrals, sets of measure, removal of the sets of measure 0 does not affect the integrals. So it does not affect these kind of things. Okay, so let us work on that now. So without loss of generality, we assume Fn converges to F pointwise everywhere. Okay. Where suppose we assume this. Now we in the proof, one part of the proof we have already considered, but I just recall it. assume so we should assume that is norm of Fn minus F goes to 0. That's the assumption. We know that it's a consequence of the Minkowski. And which goes to 0, which implies so for a P lying between this and this. Now what we have proved the necessary part. Now the sufficiency part will okay. So sufficiency. Assume this is the assumption that we what we claim is this. Is norm of so let us prove this. We use the convexity of a certain function and then also Pareto's lemma. So let us now construct a new class of functions. So observe that the function psi t defined by mod t to the power p for every t is convex. This is because second derivative is non-negative. Therefore, what we have is the following. Divided by 2 for every a b. And consequently, now we just plug in this result. Then what you get is this which implies, see, you take instead of A, you take mod A to the power P, or B, you take it for P, and then you take psi A minus psi B. Therefore, this is what you get. 0 is less than or equal to, or the consequence is that mod A minus B P is less than or equal to by 2, and therefore, which implies this is true for every AN. Therefore, which further implies now consider Hn x defined by mod Fn x for P plus mod Fx P divided by 2 minus and what one can say is that this is a non-negative function. So Hn is therefore Hnx non-negative. Now look at the limit of this. For each x, we see this. This converges to fx. Therefore, this is fx mod fx to the power p by 2 minus this is 0. Okay. So, you see that mod fx to the power. Okay. So, Hn converges point-wise this is what. Okay. Therefore, the sequence Hn this is the conclusion. Okay. Now we apply Fatos's by applying Fatos's we have integral over E is less than or equal to lim inf अच्छा okay. So this is this is what you get from, because Hn converges to mod f to the power p, so you get this. So it's simply taking limits inside. So this inequality is with, when lim inf is taken inside, all you get is an inequality, and there are examples where in some cases you cannot improve upon this estimate. Which is equal to, okay, and which is equal to, this is what we are, so Hn we replace by this is equal to integral over E with the minus sign, the lim inf would become lim sup, change over to lim sup. Integral over E and this of course is so you have, what you have is this, that is 0. See what have we got? Have got this inequality. This inequality. So we are going to we are working with that. Therefore, this implies lim sup of is less than or equal. What does this mean? This is in general greater than or equal to 0, but lim sup of this is less than or equal to 0. So together we obtain that this is equal to 0. Implication is that acceptance. That is only possible. What does this mean? That is norm of no. Okay, so we have proved this theorem. Okay, now in our example, let us see what is happening. Now you see, in our example, with Fn given there, F is identically equal to 0 and norm of is equal to 1 for every n. Norm of F equal to 0. Hence, norm of Fn consequently that is Fn does not converge to F in the LP. So that's just the going back to the example. Okay. Now what we can also prove is another condition. This is again another necessary and sufficient condition for Fn to converge to F. Next theorem. Let measurable one less than infinity. Suppose is a sequence LPE that converges pointwise to F almost everywhere, pointwise almost everywhere to F belonging to LPE it's the same precondition that we have taken in the previous theorem. Then another condition. LP if and only is uniformly integrable and tight now there are two concepts which we have already introduced earlier coming into play. One is uniform integrability of a sequence of functions. The other one is tightness of this sequence over E. Now let us just recall the two concepts and then come to the proof of this. Definition. A family F of functions on E is said to be uniformly integrable. Uniformly integrable because we are going to work on this family. Okay, uniformly integrable over E provided for each epsilon positive there exists a delta positive such that for every F belonging to the class F, if A contained in E is measurable, and measure of A is less than delta, then integral over A is less than. What it says is that the following. See, given an epsilon positive, there is a corresponding delta such that on all subsets A of measure less than delta, the integral of the entire class of functions F or mod F is going to be less than epsilon. That means there is certain kind of control over the integral all over the set E. Because once you fix an epsilon, there is the corresponding delta such that on any interval of length delta, or not interval, on any subset of measure less than delta, the integral is less than epsilon for every F. Now this is the condition that we use. Okay. Now let us use this. Okay, let us go back to our example and then see what happens. what we have said is that if such a thing happens for mod fn to the power p, then there is LP convergence of fn to. This is what we have stated earlier. Okay, now let us look at our example. So going back to the example, namely zero one, this is the function that we have looked at. Now you see, you ask the following question. I mean, this is where we have seen that fn converges to f is identically equal to 0 point. But fn does not converge, does not zero one. Now this is what we have obtained. It converges pointwise, but it doesn't converge. So let us examine whether what happens to the corresponding sequence. Now we see that observe that what is it? See, fn to the power this is equal to this is 1 by 0 1 by n. This is this. Now you see that it's quite easy to see that this is not uniformly integrated. Okay, because for any epsilon you should be able to get a delta such that the result, the statement holds. Okay, so you can always find a subset of measure less than delta on which this becomes large. Okay, right? See, on this is equal to 1, but on subset, I mean, we cannot really control it to be less than epsilon. You can always decide or find an A measure is less than delta, but not this will not be satisfied. I'll show that. You can make it as large as you want by choosing the interval to be sufficiently small. Okay, that's possible, right? Because if you take the what is this? This is equal to this. Yes, over 0 sum delta. What is this? This is equal to integral 0 to delta zero to 1 by n. So this becomes what? Delta. So this becomes n delta. Okay, n delta divided by this interval. So this is the, suppose you take a where delta is less than 1 by n. Then this is equal to n times delta. Okay, and what happens is that you can choose, suppose, can you make this arbitrarily small? It is not possible. Okay, right? Because as n becomes large, this will go to infinity. That's why it is not integral. Integral over 0 to delta is equal to integral over delta 0 to delta n to zero 1 by n, which is equal to n delta for delta less than 1. Okay. Now this goes to infinity as this would become unbounded. That's the problem. So it is not uniformly integral, right? Now we have another concept, namely what is called tightness. That is irrelevant in this example. So, a family F of measurable quantities on E is said to be tides provided for each E naught of finite nature for which is less than epsilon for every plus. So measure of E naught is finite. Now this example, so in the example we have considered, so this condition is not what matters in this case. Okay. So this particular example, that is because the E that we are considering is of finite measure. E is of finite measure, and that's the point. So we now prove the theorem. The sequence converges so we started the sequence converges pointwise almost everywhere on E 0. That's the assumption that we are making. That is infinite. No, sorry. Yeah. Now we apply Vitalis convergence here. By a corollary to വെള്ളം പോണോ equal to 0. You can only and type. This is just the statement of the corollary to Vitalis convergence. So that is one part of the statement. Now, for every n, this is okay, and therefore mod fn to the power p to the power p, which is less than or equal to 2 to the power p almost everywhere on mod f to the power p is integrable on E. Therefore, is integrable. Now you can use here. F is integrable. This is yeah. This is integrable. Uniformly and further, right, over, and that is if and only if so this it is actually this estimate which helps us to come to the conclusion. So if this is, see, this is uniformly integrable and tight, and this also integrable, and then you have this uniformly integrable, likewise tightness. So also this true. So you have this if and only if condition coming out. So that completes the proof. Okay. So thank you very much. I conclude here. We conclude this series of lectures at this stage because this is a stage where we can stop, we can go from here to develop a lot of other things. And one of the worthwhile explorations that would be worth doing is to introduce the concept of measure theory in a general setting. So here we have considered a particular measure, namely the Lebesgue measure. How far we can generalize this concept? Now this is the exploration that we would take. And my next series of lectures most probably will be trying to generalize the concept of measure, and on general sets trying to define a measure and then try to develop an integration theory which is modeled on what we have done on the real line. Now this is something forced. There you have a lot of freedom. Okay? You can choose your measure, you can choose your you can accordingly define the concept of integral and then explore what comes out of it. Okay. So we will try to generalize these ideas in our next series of lectures. So I want to put a full stop to this series at this level. So thank you very much. Hope those who are interested to know what Lebesgue measure is, what Lebesgue integration is, why the whole idea has come about, and I hope my series of lectures would be of help. Thank you very much.